Swayam Prabha. Digital India. Educated India.
Okay, today we are going to talk about adiabatic process because we couldn't finish the adiabatic work and this today's lecture is going to be talking about the enthalpy and other heat exchange heat transactions. But before that, let me take up the adiabatic work before we complete this. We could not complete it in the last class. What happens in an adiabatic process? As you can see, as you understand that in adiabatic process, there is no heat exchange between the system and the surrounding. The system is entirely insulated, and the gas, if it is doing work, that means it has to expand. So it expands on what basis? It does not have any energy coming from the outside. So the gas expands at the expense of its internal energy. So what happens when the gas expands? The internal energy of the gas is going to be reduced. So if the temperature is internal energy is reduced, what is happening is the temperature of the gas is going to drop. So whenever we have an adiabatic expansion, what is happening? We are moving from one state to another in such a manner that there is no heat exchange between the system and the surrounding, so that the work done or the expansion is done at the expense of the internal energy. So the internal energy is expended or utilized in doing the expansive work. So in the process, the internal energy of the system is supposed to be reduced, and in doing so, the temperature is actually proportional to the energy of the system, so the temperature of the system should fall. So suppose we have isothermal system, then you can see these are the isotherms, and whenever we have a change of state along this line, the PV is constant, and we may monitor the PV along one set range of temperature. And if I have another isotherm, this, if it is lower, that means this temperature is going to be higher. How can you say that? See, this P is proportional to temperature. So if the P is higher, for this is P is higher compared to this at any position, so P is higher, so this P is higher, corresponding this temperature should be higher. So this is the path along which we move when we are talking about a isothermic expansion or compression. But what happens, you see, when you have an adiabat, it is going to go not from the same change in state from, say, initial to final. If you are having a compression taking place from initial to final, it is going to be moving in a line which is in which P into V is not a constant. That is something else which is constant, because if it had PV had been constant, it should have been lines parallel like this. But it is something which is in between the two sets of isotherms, and this we call as the adiabat. And you see, when you are having in the isotherm, the P is going to fall inversely to V. But when we have adiabat, the P falls inversely to V, but V to the power gamma. So, and gamma is what? It is Cp by Cv, and that is Cp is greater than Cv. So this is going to be always a number greater than 1. So if this is greater than 1, this decrease is going to be more steep, in the pressure is going to be more steeply decreasing when you increase the volume. So this is how you can visualize. I can have a better visualization. This is going to be a better visualization of how it's going to be looking. Now what happens? When you have an adiabatic system, that means that no heat exchange is taking place, the Q equal to 0. And what happens in the process? If Q becomes equal to 0, according to first law, delta U should be equal to W. Okay. So if what is delta U? Delta, if you say write down what is the partial differential form, the change in delta U is equal to change in U with respect to temperature at constant volume into dt, in the change in internal energy with volume at constant temperature into total volume change. So what happens here? If I want to find out the total work in an adiabatic process, Q is equal to 0. Total work will be equal to the integration of Q from initial to final, and that is nothing but for an ideal gas equal to CVDT. Usually we want to take up this in the molar specific heats before we talk about the CP, but before we talk about the delta U, because delta U we are relating for CP to delta U. So if the change in internal energy, we can say that the change in internal energy is going to be, how we are going to come to this, we are going to look into it. But anyway, we are not, if we say that it is CVDT integrated over the temperature from T1 to T2 for an ideal gas, this will be the case. And for a, if CV is independent of temperature in this range, then we can write down CV delta T. So if it is an adiabatic expansion means what? That work is obviously done, volume is increasing, work is done by the gas, and the internal energy will be decreased because you are having an expansion process and the work done is at the expense of the internal energy. So expansion means it is going to be negative work because it's expansion, and internal energy will decrease. So in the process what you have, the final temperature will be lower than the initial temperature. You have to make remember that. What happens if you have a free expansion? Again, free expansion, P external is equal to 0. So P external W equal to 0. So there should not be any delta temperature change if you are having a free expansion. When you are having a fixed pressure, we can write down W equal to P external delta V, and W is again equal to the, we have said that it is equal to du, and du is equal to CVDT. So I can find out what is the temperature change from this expression by combining these two. P external dV divided by CV should give me the total change in temperature. What happens in a reversible process? Reversible process, as you say, when you are increasing the number of steps and it is going to be a continuous process, as you can see it here. If I you can visualize the adiabatic process being carried out, I have to integrate from V1 to V2. What do I do? How do I do that? For a reversible process in the adiabatic system, you can write down du equal to W, because that is Q is equal to 0, and I can replace du with CVDT. And what is W? W is minus PdV. If I replace for an ideal gas, a P is replaced by nRT by V. So I have a minus nRT by V into V, delta V, and here I have CV delta T. If I take T down in this side, this T I can take it to this side. Then I have 1 by T dt into CV. Here what do I have? I have R. I've divided throughout by R, so this is going to be molar CV, and this is going to be R because I've divided by throughout by N. So I have 1 by V dV. So now I can do the integration, and if I do the integration, I have CV, the molar specific heat at constant volume, ln T2 by T1 will be equal to R ln V2 by V1. Now you do this simplification. R is nothing but Cp minus Cv. So you put it in this, R is equal to Cp minus Cv. Now what you do, you now take the Cv this side, brings the Cv to this side, okay, and what do you get? You can divide it throughout by the Cp value, Cv value. Then what you get, if I know that Cp by Cv equal to gamma, then I can replace that by gamma minus 1. Okay, you divide all throughout by Cv, then you get gamma minus 1. If you rewrite this entire expression, and what is, when you want to take out the ln, what you write down, T2 by T1 will be equal to V2 by V1 to the power gamma. Okay, because I've changed the signs of volume here, V1 by V2, so the minus sign is gone. So I can write down the various forms in which I can write down the PV relationship. What you have to remember here, you have to always ask, you are always asked to find out the final temperature. You have to know the relation between temperature and the final volume, or temperature and volume, or temperature or pressure and volume. So if I have to have a relation between pressure and volume, so I can use this P2 V2 by P1 V1 equal to T2 by T1, and that we have in a slide for now I have shown that. So we can write down that here along this path the PV to the power gamma is a constant, so fall is much more steeper. And if you, these are something which I am writing, but until you do it is making no sense. You have to derive. I deriving and telling you how to do it, it makes no sense. So you have to have an expression in temperature and volume. You have to have an expression in temperature and pressure. You can have an expression in pressure and volume. So in an adiabatic expansion, what happens? Expansion means the final volume is going to be more than the initial volume. The gas will cool, temperature will fall. And as you do a compression, the volume is going to reduce. So final volume will be less than the initial volume, and the gas will heat up. So if you have a adiabat considered, suppose you are considering here, and you want to find out at a temperature, at a particular pressure, what is from the starting initial state at a given pressure, what will be the corresponding volume of the system. If you are doing an adiabatic process and you are carrying out a isothermic process, you see where it is cutting the excess. This is the place it is cutting the excess, and this is the place it is cutting the excess. So this is the isotherm. The volume will be higher for the isotherm compared to the adiabat, right? So the volume change from starting from the same initial state to a particular fixed volume pressure, if you want to find out, you will see that the volume, final volume associated with the isotherm is going to be higher than that of the adiabat. This is because the gas cools during the reversible adiabatic expansion. So these are the expressions you have. You have to do numericals, practice this. These cannot be taught in the class. You have to understand how to write down, how can you write down T1 in terms of the ideal gas law, T2 and in terms of ideal gas law, and take the ratios, and that from that ratio P1 V1 by P2 V2 you can write down since P2 volume is related to the temperature, as you have seen here how it's related, temperature in volume. Similarly you can find out what is going to be the, so in adiabatic reversible adiabatic condition, what you have the two the internal energy integrated over the temperature, and the work done integrated over volume equated. Because you have equated that Q becomes equal to 0, you can find out what happens if you have a constant pressure process. Constant pressure means the pressure is for an adiabatic constant pressure process. What you have, the P external becomes equal to P2, that's the constant pressure we are, that is the pin which we have put, that becomes the P2 when we are putting the pin. So this is the pin associated with the pressure associated of the gas when you have a pin. So P2 delta V is what you are going to get. Again the delta U is going to be equal to CVDT. We have not done the energetics part. We should have done the energetics first before, then only we can, then it would have been easier to discuss. Now you can understand, you have the CVDT equal to minus P2 dV means V2 minus V1. So V2 minus V1 into the final pressure, the external pressure, if it may be equal to the given pressure or a fixed pressure, will be equal to CV T2 minus T1. If you solve this, you should be able to get the conditions for whatever needs to be found out. Now note that pressure P1 is equal to greater than P2, and again the temperature is going to cool. So less work is recovered in an irreversible process. This is what I've been saying all throughout. Less work is recovered from a system when we are doing it irreversibly. So if you compare that, you will get the volumes. Since the volume is going to be less, you get sorry, if the temperature is going to be cooling down, so obviously the volume change which you look at will be different, and the volume change is going to be related to the work, and so the less work is going to be recovered when you are doing a reverse. I do not have a slide for that. I should have shown that. Okay, now this is an example which I am not going to read out. You have to do for each of the process. For each step, calculate the work done for a cycle isotherm. I'm not going to discuss this. I'm going to move into the energetics, and I leave you to read this, and these are all summaries which I have done. So you can look into this, and then we can look into another slide. Where is that? So we are going to start with the first law. We have done. We have to do talk about the say um, the heat transactions and Joule's experiment. That is very important, which we talk about. So what we have done, we have talked about CV, CP, but we have not discussed what it is. In general, what happens in a closed system when we are talking about the internal energy change, it is associated with the total amount of Q which is absorbed and the total work done. And so this is the total. If it is only expansive work, we also have additional work. Suppose you have electrochemical work and those sort of work. We are not talking about those work being there. All additional work being zero. Suppose I carry out a process in a closed system where the volume change is zero. There is no expansion. Okay, constant volume process. Then the work done, it becomes equal to V equal to delta V equal to 0. So the expansive work as well as additional work, now we are not talking, so that both the things become equal to 0. So the total internal energy becomes equal to the heat transfer at the constant volume condition. So there is no additional work done. So we can measure the change in internal energy. That will be the measure of the amount of heat absorbed at constant volume. So this is the discrete change, measurable change. We replace D by delta sign. So the heat capacity, if you want to define, it's a response function. You should remember the heat capacity is the ratio of the heat supplied to the temperature rise it causes. So heat supplied to the temperature rise it causes. So we can rewrite Q by dt. And what is Q? Q, we have said at a constant volume process that Q is equal to delta U. So if I have this specific heat as at constant volume, then this Q will be replaced by delta U. So delta U by dt at constant volume should give me the molar specific heat at constant volume. So molar, what is molar heat capacity? When you're talking about molar heat capacity, it's the heat capacity divided by the amount of substance. That means it should be per mole. So we can, molar condition comes that if you are it is per mole, so you divide it by per mole. Or if it is specific heat, it is going to be the heat capacity divided by the mass of the substance. So per gram of the substance. So this is the specific heat when we are talking about. An adiabatic warm calorimeter can be used to find out the change in internal energy. Now internal energy change, how is internal energy changing with temperature? Internal energy changes if you change the internal energy with temperature at constant volume, that is nothing but the measure of the CV of the system, the constant molar specific heat at constant volume. And if you rewrite that, you can CV dt will be equal to delta U, that will be the heat transferred at constant volume. So the heat transferred at constant volume is equal to the internal energy change, which is nothing but the CV dt for the particular process. So if the heat is added at constant volume, no work is done because volume is zero. So thus the heat added is only to contributes towards the increasing in the internal energy. So the you see the heat transferred is a measure of the increase in the internal energy of the system. CV, as you see, is a response function of the system for a given quantity of heat. Suppose some quantity of heat is supplied to two substance. The lower temperature change, whichever substance is having a lower temperature, see D is in the denominator, okay? So the lower temperature change means CV value will be higher. So larger CV value means there is a lower change in temperature in the denominator. So for the same amount of heat supplied, if the temperature change is small, then the CV is large. Okay. Now the enthalpy, will hurriedly go into the enthalpy part. I'm not going to go into details, but enthalpy is a constant pressure process. So volume change is not equal to zero, but there is going to be expansive work. So if I have to have expansive work plugged in into this, what I have no additional work. Internal energy is not equal to the change in Q. It is having some value. So it is a definition. You remember, enthalpy is a definition. From what is the definition we are having? Enthalpy by definition is U equal to U plus PV. So it's a state function. That means it is the difference, change in internal energy is nothing but the initial minus the final values. And if I want to find, it's a total differential, so I can take U plus PV and do a total differential. Will not write in this short form. We are going to write in total form, but delta U plus PV plus you differentiate with respect to P with V with pressure constant, and with volume with pressure volume with change in pressure. So this is going to be a condition which we are going to generate. But for a constant pressure process, what happens? If you can write this, you can, from the definition you are writing total differential, and at constant pressure process what happens, this becomes equal to zero. So we have the definition of how the delta change, where at a constant pressure process what happens, that enthalpy change is equal to the change in internal energy plus PdV. This is nothing but the heat transferred at constant pressure. So a heat transferred at constant pressure is equal to the enthalpy change for a process at constant pressure. Okay, so here you can understand why it is coming. Delta U is equal to U minus PV. So from here, if there is a constant pressure process, you can find out that the total change from here, you can just put this equal to zero. So it is equal to the total change in internal energy plus the work done. So we can if I do not write work done, I write plus PdV, so it should be minus PdV for work. Okay, remember that. So this is integration of delta U and delta H from initial to final is nothing but the total heat transferred at constant pressure. So the enthalpy change is equal to the total heat transferred at constant pressure. And what is that related to? That is related to the Cp, specific heat, which is delta H by delta T at constant pressure. And Cp and Cv both are temperature dependent parameters. You can measure it at using various apparatus like isobaric calorimeter, differential scanning calorimeter, These are machines you can use to find out the value of delta H. It's a standard experiment. You have other experiments also to find out delta H. Delta H is equal to the heat transferred at constant pressure. So if you have that understanding, you can understand that since Cp is defined at the enthalpy change Q at constant temperature, a constant pressure by temperature, so this can be replaced by C delta H. Delta H by T at constant pressure is the measure of Cp. So Cp is delta H is nothing but Cp dt is equal to d, the Qp. Okay, so delta H is equal to the molar specific heat at constant pressure into dt is equal to the Qp, the energy heat transferred at constant pressure. See, usually it is a function of temperature. The temperature function of Cp is usually given as A plus Bt plus C by T square, where T, A, B, C are some constants. So if you want to find out the total change in enthalpy, you can integrate from here. You can write down, you can integrate from the initial temperature to final temperature. But then if this is only possible if Cp is independent of the temperature change, independent of the temperature in the temperature range where you are measuring that, doing the measurement, like from T1 to T2. Otherwise, the Cp function has to be used in terms of the various functions of T. So you see, there's the empirical variation equation for Cp is given as like A plus Bt plus C by T square. This is the empirical expression which is obtained by through experimentation. So if I want to find out what is delta H, now I have, if I have to replace, if it is temperature is dependent on this equation, see, it is a function of temperature, so I have to take this and integrate at each of the term into from each temperature and find out what is going to be the value from for A the T initial to T minor T final, from T initial to T final for B by 2 into A. So these are things which you have to do. We are not going to do into details of this, but you have to find out if there is, what happens if there is a phase transition. Phase transition means that the enthalpy of the process becomes equal to the heat transfer. So the enthalpy of vaporization will be equal to the energy heat transferred at during vaporization, or similarly for fusion. So if I want to calculate the delta H for a heating 1 gram of ice at 0 degree to 100 degree centigrade under 1 atmospheric pressure, then what I have to do, I have to first look into ice at 0 degree to has to go first to melt to ice water at 0 degree. So the fusion of ice has to be put in, plus then I have to have the change in temperature from say 0 degree liquid to 100 degree liquid whatever water. So from 0 degree 273 to 373 into dt, that is not phase transfer. And then plus, since it is going to 100 degree centigrade, vaporization will start at 1 atmosphere. So the pressure is done at 1 atmosphere. So this will be the delta H vaporization. So what is going to be the total delta H? It will be for a system where it is heating from 1 gram of ice at 0 degree to vapor at 100 degree. What you need to consider, under constant pressure, this will be the delta H fusion plus the Cp, because delta H is Cp dt, right? But when you have a fusion, when you have a phase transition, that time you do not write Cp dt. That time you write only the enthalpy change for that process. So because it is happening at a constant temperature and process. So a constant temperature and pressure process. So you have delta H fusion plus the temperature range in which the liquid is get carried heated from 273 to 373, plus the vaporization. So if you add all of these, calculate all of these and find out, add them up, you should get the value of say delta H of the process, entire change of state. So when you are talking about Cp and Cv, you see that Cp is always greater than Cv. Now let us find out why it is greater than Cv. When you are having say heat capacity at constant volume, what you are having the same mass. Suppose it is enclosed in an insulated container, and it's a constant volume process. So volume is fixed, the container volume is fixed, and you have a fixed mass. Okay, now what you do, when we are talking about a heat transfer, we are putting in heat. What happens? The temperature rises, and the temperature rise is actually changing, the increasing at fixed volume is causing the change in the internal energy. So the temperature is risen and the internal energy of the system is increased because the volume is not going to change, right? Now, so the total amount of Q which is added is nothing but the measure of the change in the internal energy that is occurring. So that is equal to nothing but the mass of the substance which you have into Cv into dt. So that Q will be, you can calculate from m Cv dt, because we are carrying out the process at constant volume. Now what happens when you are having a constant pressure process? Constant pressure means the pressure has to be held constant. So this system can be again maybe an insulated system, but here what you have to have a piston, because until you have a movable piston you cannot control the pressure to be constant. So there is a piston, there is also a thermometer. Now you add a Q amount of heat. Again you are having a heat transfer, adding heat to the system. What will happen? The temperature also will rise, and the blade will also, piston will also move. So that what happens is, here when you are adding heat at constant pressure, then what happen, to keep the pressure constant, this volume has to increase, the piston is moving. So for the mass m, to have a fixed pressure, we have a change in internal energy. In the process we have a change in the volume. So the total change we have is the change associated with the work done, PV, because of the expansion, as well as the total energy change associated with the change in the applying of heat associated with the internal energy. So you see here we did not have any work, but H contains not only the increase in internal energy but also some amount of work. That is why when we have a constant pressure process, the Cp will be greater than the Cv, because in constant pressure process you have a scope of doing work in addition to having the increase in internal energy. But while in Cv, in the constant pressure volume process, you do not have the contributions for work. So that is the reason why Cp is always greater than Cv. Now Cp and Cv both are temperature dependent. As you can understand, it is going to be a slope of the plot between the internal energy and temperature when the volume is held constant. Similarly here Cp will be what? Cp will be the slope of the plot measured for various enthalpy change and at various temperatures. And if you see, the internal energy of a substance increases when you increase the temperature, and the increase depends on the condition under which the heating is taking place. For a present, let us suppose the sample is a gas and containing a fixed volume. The slope of this curve gives you the heat capacity at constant volume. If you see the heat capacity, the slope here and the slope here, you will see this slope is much higher than this one. So the Cp value will be, Cv value will be higher at higher temperature. Similarly, when you are talking about the enthalpy versus temperature plot, then the slope is nothing but the Cp. Then this is the slope, so this is nothing but the Cv. The slope of the tangent of the curve of the enthalpy system subject to the constant pressure plot against temperature is the heat capacity at constant pressure. The slope may change with temperature, in which case the heat capacity varies with temperature. Thus the heat capacity of A and B are different and at the 2 points, and you can see if you compare the two plots, if you plot the internal energy axis here and the enthalpy axis here, this will correspond to the internal energy curve and this will correspond to the enthalpy curve. So this is corresponding to CV and this is corresponding to the CP. You can make out the CP curve is much more steeper than the CV curve. So when we are talking about heat transaction enthalpy change for an ideal gas, we know this is the expression for enthalpy, and for ideal gas, what is PV? PV equal to nRT. So you substitute nRT here, and instead of the R is a constant. If T is not a constant, N and T is supposed to be differentiated. But if you have an isothermal process, suppose you have a gas phase reaction at a constant temperature at a given temperature, that is process is carried out at constant given temperature, then what you can see here, the T will be out. So this will be just the change in the number of moles of the gas. So internal energy, how internal energy can be related to the enthalpy change, it is for an ideal gas and an isothermic process is going to be nothing but delta U plus the change in number of moles in the particular gas reaction into RT. If there is non-reactive ideal gases undergoing heating and cooling in the closed vessel, if they are not reacting ideal gases, then we can write, we can replace this R by, we can replace this R by Cp plus Cp plus Nr. Okay, this is Cv plus Nr. Here you can write down U replaced by Cv dt. So Cv dt plus Nr delta dt. That means you can take out Cv plus Nr into delta T. So nothing, you can get here again the same expression, delta H equal to Cp dt. So the heat transactions, if you see the heat transaction, whenever you are having at constant pressure, the heat withdrawn from the surrounding, whatever heat you are carrying and taken out from the surrounding, is equal to the increase in the enthalpy of the system. And if you have a gas, ideal gas system and a gas reaction, then how is the enthalpy related to the internal energy? The enthalpy is equal to the internal energy plus the number of moles of the change in the number of moles of the gas in the reaction into RT. Suppose you take this example, what is going to be the enthalpy change occurring during a reaction of the gas molecules under constant temperature and pressure. So this is the reaction which is given. Now what is going to be the difference between the internal enthalpy and internal energy is going to be nothing but how many moles are changing, final number of moles divided minus the initial number. What is going to be the delta number of moles? Delta number of moles from here you can find out. Only the gas phase, okay? Only the gas phase. So what is going to be the number of moles change? It is going to be minus 3, because these are liquid. These are glass only. This is the liquid. So if final initial is 3 moles of gas, and finally it is 0. So the change is minus 3 RT. I hope you can understand and do some numericals on that. Now let us go into the Joule's experiment. It's a very important experiment because it is going to be fundamentally dealing with the expression of delta U. If you remember, the delta U is a function of temperature and volume. So the total differential of delta U can be written as in this form: the change of internal energy with volume at constant temperature into dV plus internal energy change with internal energy with temperature at constant volume into dt. So this is the expression we have. Now from Joule's experiment, what he did, Joule did an experiment where he had this water bath into which he had 2 bulbs in which there was a gas, and this gas, one side was at high pressure 22 atmosphere and the other side was empty. So this, what he did, he opened the stop cork and he let the gas equilibrate. What he noticed, that entire system was submerged in water and then this was in an insulated condition. So the he was reading the temperature of the water bath and trying to find out what is going to be the change in temperature when the gas expands. What he found out was there was no change in the thermometer reading. The entire thing was insulated, so there was no amount of Q flowing. He didn't. What his observation was, there was no change in difference in temperature. Though you see the volume of these two are equal. So when you open up, when the gas expands, it's initially this was the gas and this is the gas. The volume is expanded to double size. So, but he did not see any temperature difference of the water bath before and after the expansion. It's a free expansion, so work done is going to be 0, P external is equal to 0, and adiabatic system, so delta Q is equal to 0. What his observation was? There was no temperature change. So if you have the total expression of the total differential of the internal energy, this is the form you have. Now you see there is no change in temperature, that is what he's noticed. So we can say this part is equal to 0 because he did not notice any temperature change. So this part is going to 0. Now what does that mean? That means this part at constant temperature, if you think, only du will be equal to this. And what he found out that this part is equal to 0. If there is no change in temperature, what will happen? If there is no change in temperature, that means there is no change in internal energy. So the entire thing should be 0. This is, he is not seen any temperature saying this can be 0. But the temperature, the U is a function of temperature. So if there is no temperature change, that means the entire U, this part should be now come to 0, right? But if you look at this, you see it is a dV, and dV is actually not 0. dV is doubling the size. The change in volume is 2. Final is twice the initial volume. So volume change, you can make out that volume change is not 0. So what he concluded? Is maybe this is actually what is 0. That is why the entire internal energy change according to this expression becomes 0, because no temperature change is observed. So this is 0. Now since the internal energy, the temperature is not changing, internal energy also should become 0. So this part should also become 0. But this part cannot be 0 because there is a definite visible volume change, increase in volume, double the size. So what is going to happen? Then probably this value is 0, and this is known as the internal pressure. This internal pressure, according to Joule's experiment, is supposed to be 0. So Joule's experiment showed that the internal pressure, the change in internal energy with volume at constant temperature equal to 0. That's the Joule's law which he did. But the problem is Joule found this, but this is not true. What was happening is the specific heat capacity of water is very large and the gas is very small. So the difference of temperature of whatever the gas is undergoing, whatever temperature change is undergoing, that could not be sensed by water, and he could not have a more precise thermometer to see the change in temperature. So what he did not notice was his shortcoming, because of this, and the water having much higher. Water is having a heat capacity of around 4, and gas will be around 1. So so much difference in not 4,000, and so the difference is so much that the small temperature change in the gas was not even able to be reflected in the temperature rise in the water. So he could not see the temperature change. So it's a faulty experiment. But what can be fitted to is, if you consider the ideal gas. Ideal gas does not exist, but if there is ideal gas, there is no interaction between molecules, and for that we can say, for ideal gas, this internal pressure equal to 0. And you can show here, if this is the expression you have, suppose you have this expression. Now you differentiate this with respect to pressure at constant temperature. So you will have what? This as it is, and then volume change with pressure at constant temperature. But we know this from here, we know that this is 0. So if this is this second part is 0, then what can be concluded? it can be concluded that the internal change with pressure at constant temperature is also zero. So what was Joule's experiment done shown that internal energy is only a function of temperature. It is independent of volume and pressure at constant temperature. So that was what was his conclusion. It is okay when you are doing it for a ideal gas. This equation fits well, but if you do not, then you in reality we do not have any ideal gases. All are real gases, and real gases do not obey this. So real gases you do not have, you do not have this value equal to zero. So this is what is the summary of the Joule's experiment. You can go through. Now let us see how the Joule's experiment can be, expression of internal energy can be represented. How the U and H changes with the fundamental variables. U is a function of V and T. You should be able to write this. How the internal energy is changing with volume at constant temperature, keeping volume constant. How is the internal energy changing with temperature? We're giving volume constant into total change in temperature. What is this? We have just now defined this is nothing but the internal pressure, which we represent by pi t. And what is this? We know the internal energy change with temperature at constant volume is Cv. So this expression reduces to the pi t is the internal pressure dV plus the Cv into dt. So you can understand this is a general expression which you can write, and for an ideal gas, since this will become equal to zero, this can be for any general gas. Ideal becomes a condition which is special where this becomes equal to zero. So for ideal gas, delta U becomes equal to Cv dt because the internal pressure pi t is equal to zero, which is a change in volume, change in internal energy with volume at constant temperature. Similarly, this is a fallout of Joule's experiment, the fundamental variables of H is P and T. So if you want to find out the total change in P, which is also a state function, it will be the differentiation of change of H with P at constant temperature with the total pressure change, plus how the enthalpy is changing with temperature at constant pressure into dt. So you see what you have here, it's the enthalpy change with temperature at constant pressure. This is nothing but Cp. So Cp dt, and how the pressure enthalpy is changing with pressure at temperature is something we have not found out, but we'll take it for now. Like internal pressure, the enthalpy change at constant with pressure at constant temperature equal to zero. But this is something we call this as the isothermal Joule-Thomson coefficient, delta H by delta P at constant temperature, which is very important when we are talking about a real gas. So for real gas, this is not equal to zero, and this needs to be evaluated. Now, what is the internal pressure? Internal pressure, which we have just now said, change in internal energy equal to, for a general gas, it is, if it's not for ideal, then what do you have? The internal energy of the gas is the change in internal energy equal to the pi t dV plus Cv dt. Now, how is pi t changing with the volume? That is what we need to look at. For an ideal gas, pi t is equal to zero. Okay, that means U is independent of the molecular separation for a volume change at a constant temperature. But for a real gas, if du increases, is greater or positive as volume increases with temperature with temperature constant, attraction between the molecules start dominating. So pi t, the internal pressure, can have a value negative or a positive. It becomes positive, pi t becomes positive when the attractive forces with intermolecular attractive forces becomes dominant. And for such a condition to occur, what you have to have the internal energy increase as the volume change in volume increases. But as you increase the volume, if the internal energy is increasing with the constant temperature conditions, then we say the attractive forces are dominant. Then pi t is greater than 0. For you just see this potential energy diagram. This is the internal energy, this is the volume. Now when the attractive forces are dominant, then the pi t, you see the positive value of pi t, this is the slope, and that slope is the pi t, and here the slope is increasing. So the internal energy increases as the volume is increasing. This is the volume. As the volume is increasing, internal energy is increasing with temperature constant condition at a given temperature. Then you see this is the region where you have the attractive intermolecular attractive forces dominant. But you can also have a condition where the potential energy is going to fall. With that means the internal energy is going to fall or decrease as the increase in volume is taking place. You see increase in volume, here you are getting a rise, and here with increase in volume you are having a fall. So this internal energy of the system is going to decrease with increase in volume at a given temperature, provided the repulsive forces between the intermolecular forces, which is in the repulsive type, is dominant. So then pi t becomes less than equal to 0. Now this is a summary of this. Only thing I want you to try out is Cp minus Cv. From the definition of Cp minus Cv, delta H by delta Tp at constant pressure minus enthalpy internal energy change at constant temperature at given volume. You expand this. If you see this, you can rewrite this in terms of the internal energy, because we know H is equal to U plus PV. So you replace that H with respect to U plus PV. What you can write? You replace H with respect to U plus PV. So you have to differentiate with respect to, here you are replacing U plus PV. Okay. Here you replacing, then what you have, U is nothing but the total differential of U have to write down. This is the total differential of U. First you write down that it's a function of internal energy. Now you substitute these values. Substitute this value, how internal energy is changing with temperature at constant pressure. How do you find out that? This is coming from here. This is coming from here. How do you get that? You first take the partial differential, total differential of U, and then you differentiate with respect to temperature. Sorry, this expression you are going to get. This you have just come from this one. Okay, differentiating all throughout, you get this one. But how do you, what is this? We have not evaluated how internal energy changes with temperature at constant pressure. We have taken at constant volume we have taken, but what is constant pressure? So we have not done that. So whatever we have for the total pressure differential, we'll differentiate that with respect to temperature at constant pressure. So you can differentiate, this will remain intact, and differentiate with respect to temperature, this will be 1. So if then you have differential of this is going to be intact, and then V with respect to temperature at constant pressure. So if you look at this, if you rearrange this, then what you get is Cp minus Cv in the left hand side is nothing but the internal energy change with volume at constant temperature. This is the internal pressure, mind you, and a volume change with temperature at constant pressure. If you look at this, then what you see is, you can say that Cp minus Cv is nothing but the work required to overcome the intermolecular forces. Intermolecular forces, why I am saying that? Because these are the change, this is the internal pressure we are talking about, pi t, So the internal pressure is a correction which is introduced in the when the and molecules have intermolecular forces, and then you are also having a finite volume condition for a real gas. So how the volume changes with temperature. So these are actually entirely looked into as the intermolecular forces which is contributing, and then you have the one which is coming down from there is P delta P delta V by T. That means like how the expansion is taking place when you are heating the sample. So if you look at this, very closely, this is how you can write down Cp minus Cv is the measure of the work needed to overcome the intermolecular forces and the expansion per degree. So if this is the internal pressure which is associated, and for ideal gas, what happens? The internal pressure equal to 0. If internal pressure equal to 0, if you look at this expression, if the internal pressure is equal to internal pressure equal to 0, then this part becomes equal to 0. Then what you have? Then you have the Cv change in pressure, volume with temperature at constant pressure. If you evaluate, it will come to PV equal to nRT. So nRT by V is what you by P is what you're going to look at, and differentiate that with respect to temperature at constant pressure. What you get is this, and then there is a P which is outside. It's going to cancel. So what you get is Cp minus Cv equal to nR. You need to practice this, otherwise it is, for me, I'm just going through, it is not making any sense. So for a liquid and solid, the change in volume with increase in temperature at constant pressure is very, very small. So that is the reason Cp and Cv are almost close in a solid or a liquid system. So this is a summary of all the changes which we can look into. I want you to practice. Go ahead and practice how each of the variables are changing with respect to the fundamental variables of that particular system, how U is changing with temperature and volume, and how the U is changing with temperature and pressure. Please do this. This is one thing which you should always practice. If you practice more of the partial differential, the better it is. Now let us see one example. Variation with temperature. What happens? How the temperature U varies with temperature. We know from the expression that this is the fundamental equation of delta U, total differential of total delta U. Now here we know this is Cp, Cv. This we can this part can be replaced by Cv. So what is now you have Cv dt, internal energy change with respect to volume at constant temperature into total volume change. Now look at this. What do you, if you want to find out how the internal energy changes with temperature at constant pressure, so you differentiate this with temperature at constant pressure, you get Cv plus what you have, this is as it is, into change in volume with temperature. How is change in volume with temperature known to us? We know that isobaric expansion coefficient is nothing but how the fractional volume changes with temperature. So this is the total fraction of change 1 by the total volume into the change in volume per unit change in the temperature at given pressure. So if you can find out that, then you can replace this here. You can replace this here. So you get a new equation of alpha T delta U by delta VT plus Cv equal to this part. And this again is nothing but the kappa pi T, this is the internal pressure. So the internal pressure, this is the internal pressure, and this is nothing but, if I can write down this here, then it will be alpha into V. So alpha into V into Cv U by T at constant temperature is nothing but pi T alpha V. So these are the simplifications which is done. It is doing in the class is very boring, but still you keep doing. So this is what we have got. A large alpha means it's again a response function. Large alpha means it's responds strongly to change in temperature. For an ideal gas, mu J T equal to 0. So from this expression, this is what we have evaluated so far. How temperature, internal energy changes with temperature at constant pressure. So usually we know this is equal to the volume is equal to Cv, but here we will show for a ideal gas for which the mu Jt is equal to mu T, the internal pressure is equal to zero. For that, internal energy change with temperature at constant pressure is nothing but the measure of the Cv of the system. Similarly, you can find out, you take volume as a function of temperature and pressure and try to evaluate in terms of the kappa and the alpha by total differential and then replacing. I'm sure you can all do it. If you want to find out what is this, finally what you get, alpha is the fractional volume change with increase in temperature or decrease in temperature, whatever you call it, with change in temperature at constant pressure. So since we can use the ideal gas law, please show that for an ideal gas, kappa T from this expression is equal to 1 by P. Please do it. Similarly, you can have how the pressure changes with temperature. How the pressure changes with temperature, here again we apply the cyclic rule. Pressure being function of temperature and volume both, then we can write how pressure is changing with temperature at volume constant, then how temperature is changing with volume keeping pressure constant, then we are how volume is changing with pressure keeping temperature constant, should be equal to -1. So I can find out what is the change in pressure with temperature at constant volume. That will be equal to 1 by this Cp into dV dP at constant temperature. I hope you are following what we are saying. And lastly, I would like to take up hurriedly the enthalpy changes. Enthalpy is a function, main function of enthalpy is pressure and temperature. So you differentiate with respect to pressure, keeping the temperature constant, and then differentiate with respect to the temperature, keeping pressure constant. If you look into the expression, the total heat transfer at constant pressure is nothing but the delta H, which is equal to CPDT for our case. Similarly, what we have been talking about in the previous class also, we were interested to find out, I said, isothermal Joule-Thomson coefficient. Isothermal Joule-Thomson coefficient states that the change in enthalpy at given with pressure at given temperature can be found out in a manner that if you use the cyclic rule again, how's the, since H is a function of P and T and each of them are themselves function, so how the enthalpy change is changing with pressure at constant temperature, and how pressure is changing with temperature at constant enthalpy, and how the temperature is changing with enthalpy at constant pressure. If you, thing which I want to introduce is this part, how the, if you take it to the other side, what you get this will go up, so this will get reversed. So delta H with respect to delta P at constant temperature is nothing but this term, change in temperature with pressure at constant enthalpy, and this is usually used in the Joule-Thomson experiment, and so this is known as the Joule-Thomson coefficient, how the temperature is changing with input of pressure at different at constant enthalpy. So I leave you to these things to be derived by you. Please do it. It is me doing will not serve any purpose. Okay. So if you are done, then we can finish this off. So thank you.